preamble, I guess, but anyway, that's fine. No matter. So everything that we've done has been in terms of some velocity along a streamline. Those streamlines can be straight, or they can be curved. And what we can do is we can, if you wanted to, we could define a velocity which is along the streamline, which is tangential to it, and also a velocity which is normal to it, which of course has to be zero, as we said before. But what we can do is we can define a vector which defines each of these components. So the vector S is just a vector, the orientation of this direction which the flow is occurring in. And what we'd like to be able to do, we've used it in Bernoulli, we've used it to be able to calculate what the streamline velocities are because we've kind of dealt with that. And if we remind ourselves, when we've been talking about Bernoulli, we have basically set ourselves up so we have some of the forces, typically along the streamline, have been equal to mass times acceleration. We've typically divided this force as a force per unit volume of the fluid that's flowing. And so this then becomes kind of mass over volume becomes a density. And so what we've done, this is the streamline acceleration. And so what we've done is we've taken this and we've taken the change in velocity with time is equal to, we can do what we've done with before, the change in velocity along the streamline as a function of time. And we can also multiply by, this is the only relevant term because we've always said that for Bernoulli it has to be steady state. We could add the time part to it as well. And then this is actually the velocity along the streamline. And so this is equal to the velocity times change in velocity with location. Oops. And we can also write this as the change in location with v squared over 2. So that's where that term comes from. So in this case, we've chosen z, but this would actually really be the streamline direction. So this should actually be, if this was along the streamline, this would be s, and this would be s, etc. And this would be the velocity that we define across the streamline. So this is the basic relationship. That's all we've messed around with so far to be able to get the expressions that we've dealt with. And the two expressions that have come directly out of this are the ones for the Bernoulli along the streamline and Bernoulli across the streamline. And just to remind ourselves what those are. This should be streamline, I guess. But let's not worry about that for now. Rho G minus rho AZ. So you recognize this. And so this value here is exactly this acceleration. So that's the basic relationship that we worked from Bernoulli. And what we can do is we derive this, but let's just recall it, is that along the streamline, we have what? We have this term becomes, once we manipulate it, P over gamma plus elevation is plus, because of a sign change, doesn't matter, v squared over 2g. And this equals a constant, right, along a parallel to our streamline. And if we look across the streamline, we have what? Same terms, plus elevation, plus a little bit more of a complicated term. It's an integral v squared over r, uppercase r dn, is equal to a constant as well. So those are the two expressions that we had for this. So this one here, this represents a streamline acceleration. So this term here is representing the acceleration along the streamline, as we can see just from the kind of collection of these individual terms. And this represents the centrifugal acceleration. In other words, if you're spinning something around your head and you have to apply a force to keep it in that tight rotation, this is basically a centrifugal force. And so what we could do is at any point that we choose here, we could figure out exactly what this velocity along the streamline is, and we can calculate what the acceleration is just from knowing that velocity. And also, if we look at this point here, relative to some radius to the center of rotation and some direction, which always, by the way, points to the center of this rotation, always points inwards, allows us to be able to calculate what that centripetal force would be if we, again, know what this velocity is. And so what I don't really want to do is go through the derivation, but we can describe a long streamline, no, let's not call it, let's call it a streamline acceleration. Which we'll call, and the book calls, A sub s. And it is equal to the change along the streamline of v squared over 2 times a vector plus the change, the velocity, again along the streamline squared over the radius of curvature multiplied by, sorry, I messed this up. This should be along the vector along the streamline, s and n. And so that's kind of a standard result, but this is what's referred to as the convective acceleration. And this is referred to as centrifugal acceleration. So it seems kind of esoteric, but the convective acceleration basically is saying that instead of me walking across the room and knowing how quickly I accelerate and being able to calculate the forces I have to apply in my legs to move me, you sitting there can see how quickly I move across the room and how quickly that velocity changes, and you can calculate the same forces from that. Basically, this is what it is. And so that may seem a little esoteric to you, but let's just go through a very quick example to kind of illustrate the point. And that is, for instance, if we had a system that we drew, it's very, very straightforward, right? Let's say you have a streamline velocity here. We have it rotating around some point. So this is, I guess this is r. This is our x direction. This is our z direction, positive upwards. And let's say that at this point the velocity is equal to, I put a number down, choose any number, 1 plus 2x. Kind of a contrived example. So in other words, at this point here, it's equal to 1 because x is equal to 0, and you go further to right, it increases linearly and goes faster. Don't know if that's an admissible velocity field, but what would be the magnitudes of these convective accelerations if that's the case? Well, the convective acceleration s is going to be equal to, remember, it is a vectoral quantity, so it's equal to the acceleration in the x direction, acceleration in the y direction, acceleration in the z direction. And it's given in terms of the change in the magnitude of this value squared. I didn't do that, so I wrote this out incorrectly. That's fine. This term is not what it should be. Forget that. It is velocity, well, actually it's the same. So actually velocity times dv, ds, right? We know that we can write, it's just easier to do it this way. We know that we can write the change in v squared over 2 is the same as the velocity times dv ds because we alluded to it up here, right? So it's just a different way of writing it. It's easier to do it that way. So if we do that, let's just write out what this expression would be. the velocity is going to be equal to, this is the velocity in the x direction along the streamline, so the velocity is equal to 1 plus 2 times x. The derivative of that velocity, which is along the streamline, is going to be just 2, because the streamline is aligned along the x direction, which is just equal to 2. And it's going to be multiplied by the vector, which is along the streamline. So what is the vector that's along the streamline? This is the streamline vector here. So it's aligned directly along the x-axis. It has a 0 component on the y-axis and has a 0 component on the z-axis. So this value, which would be just this vector s, is going to be 1, 0, 0. So that's what this term is here. So there's a derivative along the streamline and a magnitude that is oriented, and the component due to the centrifugal acceleration is going to be the same velocity, which is going to be v squared, which is going to be 1 plus 2x, all squared. Note that this isn't dimensionally consistent, by the way. It's equal to r, is the radius over which it's turning. And it's multiplied by this vector, whatever the position vector is in the n direction. So it's nothing more than that. And you'll see this example in the notes as well. So what's n? N is directed perpendicular to the flow line. It has to be oriented towards the center of rotation, and so it's in this direction. And so what's the magnitude of this vector, which has, by the way, these have to be unit length, length 1. It has to be oriented along z, so the component in x is 0, the component in y is 0, and the component in z is 1. And so that would be the convective acceleration. So the acceleration x is just this top term, the acceleration in y is 0, and the acceleration in z is just going to be this term. So you'd only end up with 2 terms and the middle one 0. So you can always calculate the magnitude of these accelerations from knowing the velocities. So the mechanics of doing that is not so straightforward, maybe, but it's important. All it's saying is that if you know what the velocity field looks like in space, then you can calculate what the particle of fluid would experience as it goes around a bend, and that's really what controls the flow. And so that's our interest in being able to define, for instance, convective acceleration. So it's all related to magnitudes of velocity changes, accelerations, and how they are reflected in the reference frames that we choose. And so if you look at these, you'll see some stuff. This is for this. So if you want to look at it in a more complicated fashion, you can. I think you should just accept that this is the expression that we dealt with. It's a convective acceleration, a centrifugal acceleration. If you want to figure out exactly how it happens, then that's okay. But I think probably you might want to just accept that that's the case. So it seems esoteric, but it's important for us to use because when we start looking at flows in fluids, that acceleration is what is the essence really of defining forces which apply on structures. So if you turn a hose onto the wall and calculate the force that gets applied on that wall due to killing the velocity on that hose, it's really the convective acceleration that you're changing, the convective deceleration, which represents that force. And so it's something that's kind of fundamental to what we're attempting to do. So what we have talked about so far has primarily been related to streamline behavior. And we said last time that what we have, if we think of, for instance, our example where we have a weir, and we have flow occurring across the top of that weir, then what we can do is we could isolate the flow between an upper and a lower streamline. And if we do that, then we know that this has to be a boundary over which no flow occurs. This has to be a boundary over which no flow occurs. And that this area times velocity and this area times velocity have to be equal. So that was our constraint that we had put on Bernoulli's expression. So even though when we're talking about Bernoulli, we've kind of worked along streamlines to be able to figure out exactly what the behavior is, implicitly we've kind of been talking about control volumes. And if you remember the example we did with the jackass video, we took a control volume of this pipe which was coming down vertically, and we took a kind of control volume that included this guy sitting on it, holding on to it, including where it hit the ground, and we looked at the forces which were applied by this jet of water impinging at v squared over 2g to be able to calculate the forces that were applied to this. So in some respects we've taken control volumes before. What we should look at now is a more formal way of looking at this, and the more formal way of looking at this is that we can look at control volumes, if you remember this figure we started off with, in a variety of modes. We can look at them as stationary control volumes that don't deform. We can look at them as non-deforming control volumes that relative to our frame of reference either move or don't move. A jet engine relative to you sitting on the wing or in the cabin next to the wing doesn't move relative to you, but it certainly moves relative to the ground. And also ones which deform with time. And the formalism that we can use for that, we need to use this idea of frames of reference, which we've kind of spent the last period talking about, is Reynolds transport theorem. And it looks kind of complicated, but it really is relatively straightforward in terms of its components. You'll recognize some of these components now. This is the material derivative, which is attached to something and says relative to what that body is doing, whether it's changing in some way. This is an integral over a control volume, which says the change in mass within the system, or change in the quantity within the system. And this is a term that represents the flow across a control surface, which says the change in the number of marbles you have in the system is equal to the number of marbles you have within your control volume minus the number of marbles that leave your control volume across the surface. It's really just an accounting deal. And so what Reynolds transport theorem allows us to do is it allows us to define an extensive quantity. And that extensive quantity can be something that we'd like to be able to do a conservation of, an accounting for, if you like, in terms of how much is leaving the system versus how much is accumulating in the system. And that quantity can either be mass, if we want to conserve mass, how much water goes into the system versus how much water goes out. The subtraction of those two amounts is the amount that accumulates by definition. We might also want to account momentum as one of our quantities when we're dealing with, basically Bernoulli's expression is looking at changes of momentum in the system. And we also might want to look at conservation of energy, changes in energy, if we're looking at machines, for instance. And so Reynolds transport theorem, although it looks kind of scary and complex, allows us to be able to, in a general way, write a conservation equation that basically says, if overall that quantity in our system doesn't change, the amount that accumulates in our system is equal to the amount that goes in minus the amount that goes out. It's nothing more than that. And that amount could be either an amount of mass, it could be amount of momentum, or it could be amount of energy, but in either way we can account for it. So this is referred to the extensive quantity, doesn't matter what the term is. And this other quantity, which we use in the expression, is going to be equal to the extensive quantity per unit mass that's in our system. So it's the value divided by mass. So in our case, if we're conserving, so this is mass conservation, this is momentum, and this is energy. And so the next 3 weeks we'll talk about each of these in turn. Actually, we're talking about mass now. So if you divide each of these by m, you end up with 1. So this is going to be b. This is equal to uppercase B. And so what? Momentum divided by mass is equal to just velocity. And kinetic energy divided by mass is going to be 1/2 mv squared over mass, which is equal to a half v squared. And so what we can do, since we know what the value of this b is, we can throw it into here. And all it allows us to do is to do it for each of these. Use this as a general expression. This almost always will equal 0, because that's the system we choose to look at. And we can look at how these two values change. So that's really what it is. So don't get hung up on the fact that it looks kind of bizarre. If you dissect what each of these components are, then this is just the amount that accumulates in the system. And this is the amount, this is, if we're doing mass, this is mass in minus mass out. So nothing more than that. And we'll write it in a somewhat simpler way, because it's easier and I'm sure you'll use it in that way. But it basically looks at this idea here. You have a control volume. This is the control volume we drew around the jackass guy, or the weir that we drew up at the top of this page, which is now off the page. And we can look at the amount that goes across this boundary in a given period of time, which is this green material. We can look at the amount that comes out on the other side, and that's exactly what this term is. If you look at what this term is, this is a velocity times the normal to the boundary velocity, which in other words is saying that there's a certain velocity that comes out here, which is this velocity v. The only way that we can, instead of describing this as a vector with 3 components, is we can look at one value, which is the amount that comes off normal to the boundary. So the amount that comes off normal to the boundary is a unique amount. It's a scalar value. It's normal to the boundary because we've defined it that way. So you only actually have to define a mass flow rate or a velocity. You don't have to define what direction it is because the direction is already defined because it's normal to the boundary. And so the dot product of this velocity, which might have components in x, y, and z, in this direction is this normal to the boundary velocity. So this here is Vn, normal to the boundary. So if you don't like the math so much, then think of it that way. Okay? So we're going to use it first to deal with mass conservation. So we're going to choose the value of b to equal mass, as we said. And if we do that, we can make these substitutions for uppercase b and lowercase b back into this expression, because it's just a general expression. And if we do that for mass, we end up with b is equal to 1, b is equal to 1, and this mass is equal to lowercase mass. We're going to take it equal to 0 because it doesn't change in time. And we end up with maybe a slightly simpler expression. And this slightly simpler expression is easy for us to manipulate if we choose to do it. We can write it in a slightly different way. And a slightly different way that we can write it in is going to be, whoops. So what's this? So let's talk about conservation of mass. So rather than being esoteric as we were before, we're going to write that we're going to move from being esoteric to being something else. What do we have? dA equals 0. So that's our expression. So this is on a control volume. This is on a control surface. And so all we're doing is we're making a control volume. This control volume is this, and the surface of this is what we call CS. Right? This is just the integral. So what is an integral? Well, it's just a summation, right? It's no different from a summation. So what we could do, what can we assume? Let's assume that density is constant. So if we're looking at a fluid, so if density is constant, then what can we do? We can take this out of here, right? So we have a density. Oops, I left off a rate of change here, right? We have a density times an integral over a volume, over control volume. So what's the magnitude of this value here? It's just the volume, right? Nothing other than this volume that we have for our control volume. So we have that. We're adding to this value across a boundary. And so what we could do is, if you prefer to, you could think about this control volume as looking like this. So this is our control volume. This is our control surface. And let's say we have a flow that's going through this at some velocity. Not a volume, but a velocity. So the through scores are always the volumes. So what is, this flow happens at some density. What's the value of V dot n as we go across this boundary? Well, the velocity is in this direction. The normal to the boundary vector n is in, oops, is in this direction. And so the dot product here, V dot n, is equal to minus V, right? So if you have a velocity, if you have a direction here, and you have a velocity which is parallel to that, the dot product of those two vectors is equal to the positive value. The n vector is always 1, and so the positive value is always equal to the positive magnitude of that. So it's equal to 1. If the outer normal to the boundary is this direction and your flow is in this direction, they're in the opposite direction of each other, and so the values of those vectors relative to each other, the dot product is equal to minus 1. And so this is the magnitude of that dot product. If the same velocity comes out of the downstream side, and the normal to the boundary velocity vector is on this boundary in this direction, then here V dot n is equal to plus V. This is a vector. It would be units. Vx is V, Vy is 0, Vz is 0. And the normal to the bound, well, you can get it, right? So the velocity at this point is going to be what? Let's call it velocity 2. V2 is going to be equal to what? It's going to be equal to V, 0, 0. And the normal to that boundary is going to be what? It's also going to be equal to 1, 0, 0. Take the dot product of those, you end up with V times 1 plus 0 times 0 plus 0 times 0. That's all it is. So what you can do is you can help yourself by thinking that this value here you can think of as a scalar value. And if it's flowing into the volume, then it's negative velocity. If it's flowing out of the volume, normal to the boundary, it's positive. And so if you do that, you can take this expression, well, let's write this out again. This is the control surface, density times V dot n dA. Of course, that's not much easier. But what have we got here? We have, I missed out this term. So we have, this is our new expression. Rate of change with time of the product of density times volume plus this term here. So what is this? This is a mass, this is a velocity, and this is an area. So density, sorry, it's not it's a mass, it's a density times a velocity times an area. Velocity times an area is a volumetric flow rate, which is meters cubed per second. Kilograms per meters cubed per second is just mass per unit time. Mass rate. Mass flow rate. And you can check the dimensions on this. And so what this is, this ends up being mass flow rate. They all have to be homogeneous in terms of dimensions. So if you want to think of Reynolds transport theorem in this way, it's probably much easier to do. Certainly all the Most of the questions you have to do will only rely on it looking like this. And if you want to, you can write it in a slightly different format, which is probably worthwhile doing. And that would be that if you take the differential here and you just differentiate by parts, you can do it for the case where it's equal to constant density and the volume changes. This is just differentiating by parts, plus constant volume and the density changes, plus m dot mass rate of change is equal to 0. So that's our fundamental expression that we want to deal with. So this is basically an accounting for what goes across the boundaries of the control surface, nothing more than that. This is accounting for the fact that this has a volume, and if you want to stuff air into a tire, well, the volume of the tire doesn't change very much, but certainly the density of the air changes with time as you put it in there. And so this would be a fixed control what do we call it? Non-deformable control volume. In other words, a tire which doesn't change much, but a compressible fluid, comp fluid. And this would be the converse. This would be a deformable control volume and an incompressible fluid. So we can allow for all the cases that we deal with. Is that gonna, why did it do that when I don't really want it to do that? I'm not sure. Oh, we're at the end of that thing. Sorry. Can you see underneath that? I don't have, I think if I, no, what? I don't know what any of these will give me. Oh, geez, that's relatively innocuous. I don't know why it all of a sudden came on now, but is that always there? I don't know. So that's basically what we're doing. So this is the accounting. So we've gone from this complex kind of integral equation, which is nice, to something that's relatively straightforward. And this is mass rate in, sorry, that's right, mass rate out minus mass rate in. So if you want to use this expression, you just have to be careful with your signs. You can absolutely use it for all the examples we talked about here. The important signs here are that m is positive for flow out, and m is negative for flow in. And so that's the sign convention you have to make. So we don't really need to use Reynolds transport theorem, but that's where this comes from. We'll use it to get the conservation equation for momentum and energy as well, but it really boils down to something relatively straightforward. And again, I'll say this again. This case represents the case for putting fluid into a bucket, where if you take the control volume at the surface of the fluid, the volume of that fluid rises with time, and so the volume of the control volume changes with time. So volume changes with time, but the density of the fluid doesn't. This represents the case where you're putting gas or air into a tire. The volume of the tire is essentially constant. Imagine it's rigid, but the density of the air changes. You put more air into it, it has to get more dense because you physically put more mass into it. And the rate at which you put mass into it controls how quickly these change. A positive value of volume change is getting bigger. You need to know that. A positive value of density change is getting higher density. That's our sign convention. And based on that, we should be able to solve any problem. So we won't get to it today, but let's deal with it next time. I mean, a simple exposition of this is given in these couple of examples. Actually, let's just do it. I mean, this is just a couple of examples to be able to say exactly what happens if you have flow going into here, you shut off the valve here. How do you account for that particular case using this value? It's a rigid container. It has no volume change, so you'd expect that this value should be 0. Right? This is a steel container. There is a mass flow into the system. It's physically coming in here, and so the mass flow would be equal to what? It would be equal to the velocity 1 times the area at 1 times the density, which would be the mass flow, so you know that value. It's into the system, so it would be negative And this is the initial volume of this container, which is this. And you'd expect that the density would change with time because you're pushing something in, you're only accumulating stuff and nothing's coming out. And therefore, what you'd like to know is how the density changes with time. And so if you write this in this way, then you can just manipulate it to be able to figure out exactly what the final density of this system is as a function of the initial density, which we would know, the velocity at which you're putting it in, the area of the nozzle, the density it goes in at, and how long you do it for. The longer you do it, the larger the final density you'd expect to be. And so Reynolds transport theorem is just a way of doing that. Okay. So it's an important concept in what we're doing. So you don't need to necessarily revert back to understanding what this expression does, but you might be more comfortable using it in the form that we talked about here, and that is just to realize that this expression is a surrogate for this behavior, so long as you remember what your conventions are. Increasing volume is positive, increasing density is positive, and mass changes, if they're flowing in, it's negative, and if it's flowing out, it's positive. And so we'll talk a bit about that next time. Okay?